In this lesson, we'll be learning about something called non-conservative forces and how they relate to the total mechanical energy of a system. So first, let's talk about conservative forces. So conservative forces convert one form of usable energy into another, and it typically has an associated potential energy. So if you think about the forces that we've encountered so far, we have gravity, spring force, we're going to eventually deal with the electrostatic force. These three forces and others that we've encountered have an associated potential energy. So there's a gravitational potential energy, there's spring potential energy, and there's, of course, electrostatic potential energy. Non-conservative forces, on the other hand, convert usable energy into essentially unusable energy. So primary examples, of course, being friction and air resistance. These reduce the mechanical energy available to the system. We often think of this as the system losing energy because of one of those forces. Also covered in this lesson is the learning objective. I can explain how conservation of energy law is still valid in the case of non-conservative forces. Because previously, we've talked about the law of conservation of energy and said it wasn't valid in the case of friction, but that was more that we weren't accounting for it. Energy is still conserved. It's just that some of that energy went into thermal energy or went into the motion of the air. Moving air particles around does take energy. And if our model doesn't account for that, then our model for the conservation of energy isn't completely valid. Now, that doesn't mean it's useless. We can come up with good estimates or come up with approximate values, but it's just not 100% going to be correct. So what we're going to try to do here is identify the cause of energy loss in a system. So make sure that we understand where the energy is going and be able to explain why the law of conservation is still valid in this case. We just have to make an account for the amount of energy lost or amount of energy transferred to, like, thermal energy, for example. Let's take an example here. A car has kinetic energy, but when the brakes are applied, the kinetic energy seemingly disappears. Now, we know that it doesn't actually just disappear. We know it becomes thermal energy, in fact. So here is an image of the brakes of a tire. The brakes are these little pads right here that clamp down on this disc. This disc is not usually red. That is just a piece of metal. It is glowing red because these pads are rubbing against the disc, and it's undergoing so much friction that it's heating up the disc high enough that it would just completely break or melt. It is incredibly hot that it's going. And over here, we have an image of what this looks like at the microscopic level, because a lot of this is about relating it to where is that energy going at a microscopic level. Remember that temperature is just the average kinetic energy of all of these particles here. So when you heat something up, you're just causing these individual particles to move faster. And here is another image. Even if they're not like air particles that are moving around and bouncing, objects can still have a lot of kinetic energy, even when they're just one piece, because they jitter in place. This is kind of a simulation of a larger molecule that is not at zero temperature, that is not at 0 Kelvin, which is the lowest temperature possible where it'd be absolutely still. It has some kinetic energy, and it is jiggling about. That motion there is energy. Okay, so it's kind of obvious when something gets hot. But what about if something does not get hot? For example, if we had a parachuter, the parachute and the person reaches terminal velocity. They're losing gravitational potential energy, and that energy doesn't seem to be going anywhere else because at terminal velocity, they're not going any faster. The velocity is constant. So they're not gaining kinetic energy, but they are definitely losing gravitational potential energy. So where is that energy going? Well, it's going into the air particles around it. Originally, the air particles are just chilling here, and then this person goes through them and has to push them out of the way. That causes a lot of force to be applied on them, and they gain some kinetic energy. You just don't see it that much, and also, you're not able to observe the heat that is generated because it is a small amount of heat just spread out over a large amount of particles, and they mix with the air. So it's not like you'll be able to feel a higher temperature air region because a parachuter fell through it. But we can take this to the more extreme. If you had an object, like say an object is going around the Earth in orbit, and then it descends from orbit, so it goes from space into the Earth, you get essentially a meteorite. And we know that those, if you've ever seen a video of those are fiery balls of matter. So, I mean, there's some kind of like piece of metal or something, but it's going through the air and so fast that it is generating lots and lots and lots of heat that it seems like it's on fire. So that would be a more extreme example of the parachuter situation. So the air is technically getting a little hotter. It's just, it spreads out and diffuses with the rest of the air so quickly you wouldn't notice. So we need to talk about closed versus open systems. In a closed system, energy is not leaving or entering the system. In an open system, it's allowed to enter or leave the system. Conservation of energy is only valid in a closed system. So basically, if you account for all the different sources of energy and where they went, then you can use conservation of energy. But an open system, you're essentially saying that some of the energy is gone. That just means that, okay, all the energy before is not going to equal all the energy final unless you again account for, so all the energy initial equals all the energy final plus any energy that left the system. If you can account for that, if you can account for the energy that's leaving the system, then now that energy that left the system is actually just part of your system. So you actually did just have a closed system to begin with.